Supercells are the storms every chaser dreams of intercepting, but spotting one early can make the difference between a successful chase and missing the show entirely. Radar provides some of the earliest clues that a storm is transitioning into a supercell, often long before dramatic visual structure appears. In this episode, we're breaking down the radar signatures that signal supercell development and what they mean for storm chasers in the field. If you want to know when a storm is becoming something serious, this is where to start. I'm Gabriel Harbor, and you are listening to the Storm Chaser Coaching Podcast. Before we dive into the questions with Coach Trey Greenwood, there's a link in the description where you can get the cheat sheet for this episode. Cheat sheets contain all of the notes we use to build out each podcast episode, and if you click that link one time, you'll unlock access to the cheat sheets for every single episode we ever have or ever will record. Trey, first question, what defines a supercell and why are these storms so important to storm chasers?
So a supercell is a storm with a rotating updraft. Your general thunderstorm that you might see in the summertime does not have a rotating updraft in most cases. It's just a pulse thunderstorm, and the precipitation basically falls right underneath the updraft base, and they tend to rain themselves out in a very short amount of time. Supercells, on the other hand, have robust rotating updrafts, and because the updrafts are often tilted, that displaces the precipitation from the updraft region of the storm. That allows them to live a lot longer and produce significant severe hazards. The vast majority of tornadoes tend to come from supercell thunderstorms, as well as things like very large hail and significant damaging winds. Those are often reserved for those supercell type thunderstorms. They are the holy grail for storm chasers, and they're going to be some of the most robust storms you'll see.
Now, what type of environmental conditions typically support supercell development? I know there's no one size fits all, especially when you factor in things like elevation and what season of the year we are in, but typically speaking, what type of environment are you looking for if you want to see supercells develop on a given day?
You need some sort of instability, so you need the atmosphere to be unstable, at least a little bit. Like you said, there's no one size fits all here answer. We can have supercells in a limited instability environment. We can also have them in extremely strong instability environments. But you need at least some instability to support supercells. You also need the atmosphere to have strong deep layer wind shear. That's the changing of the wind speed and direction with height. And you typically want those winds to veer with height, meaning that they turn in a clockwise direction as you go up in the atmosphere. So say your winds are out of the south at the surface, you would want your winds just above that to be maybe out of the southwest, and then your winds in the upper levels of the atmosphere to be more out of the west-southwest or west. Those winds are turning in a clockwise direction with height. That tends to favor supercells. Of course, you need other things like a good amount of moisture, especially in the low levels. That's that juice that is fed into the storm that it needs to survive. And you need a source of lift to actually initiate these storms. So a storm system like a trough coming in, some type of boundary, terrain, etc. But you really need an environment that's somewhat unstable, and you need it to have fairly strong deep layer wind shear.
Now, if you are finding this podcast episode helpful, you're newer in your storm chasing journey, or you're just refreshing on the basics before storm chasing season, our Discord community is a great place to continue sharpening that iron, so to speak. Once you join our Discord community, you'll have access to all of our various channels where members are chatting about everything related to severe weather, and we'll also send you a message about something called the Chaser Academy, which is our premium subscription product. We have weekly group coaching sessions where coaches like Trey go in depth on topics that we can't quite do on a podcast episode because they contain a lot of visual elements and it would simply go on too long. No one wants to have a 50-minute podcast episode. Most people aren't savages like that. I know some of you probably would, but we will send you a message telling you all about the Chaser Academy once you join our Discord community. Link for that is in the description. All right, Trey, what reflectivity changes signal that a storm may be transitioning into a supercell?
So the most telltale sign is that you start to see more of a kidney bean shape on radar. The initial updrafts might be small and they might be just going up, but if you have a strongly sheared environment with strong deep layer wind shear, oftentimes you'll start to see a kidney bean shape. So a little bit of curvature in that storm. That can tell you that the storm is starting to rotate. You'll also see very strong reflectivity gradients going from just outside the storm to in the precipitation region of the storm. So you might see very heavy precipitation in the core of the storm on the very edge of the reflectivity region where the storm is showing echoes. And then right outside of that in the clear air, you'll see no precipitation echo. So that's a very stark change in reflectivity on radar in a very short amount of time. And that is usually a sign that your storm is quite robust and perhaps is turning into a supercell. Sometimes you might see a hook echo develop. That tends to be a little bit farther along in the process. But you may see a hook echo develop, that appendage that looks like a hook on the southwestern flank of a typical southwest to northeast moving supercell. Those are the main things as a storm is getting going that you'll see that a storm is maybe transitioning into more of a supercell structure.
Now, this next question is one of my favorites because I love the nickname that we give to this storm feature. What is a V-notch on radar, and what does it tell us about storm structure?
V-notch is, if you ever heard the term flying eagle, it's the same thing. So you'll see the precipitation getting vented off away from the updraft of the storm on the southwestern flank, again, of a typical storm that's moving southwest to northeast or west to east. You'll see the precipitation kind of form a V shape. The strongest reflectivity echoes will start to form sort of a V shape, or it might look like a flying bird or flying eagle, hence the name flying eagle, or again, a V shape, hence the name V-notch. So that is a sign that you have a very robust updraft. You can think of an updraft, a really strong updraft, as an obstruction to airflow. The air can't go through that updraft, at least the core of that updraft. And so what it does is it's diverted around the center of that very strong updraft on both sides. That creates that kind of V shape that you see in reflectivity. It doesn't necessarily tell you that your storm is a supercell per se, always, but most of the time it will indicate that it is a supercell and that you at least have a very strong updraft and that storm may be intensifying.
Now, how can velocity data help confirm that a storm is becoming a supercell?
Velocity data, if you start to see increasing rotation, so a velocity couplet where you have inbounds and outbounds right next to each other. Inbounds are the green pixels on radar moving toward the radar. Reds are the outbounds, targets moving away from the radar. If those are oriented such that you have a couplet where you have greens right next to the reds in a very tight area, and you can see that you have counterclockwise rotation in that, that is a sign that your rotation is increasing in the storm. And oftentimes the rotation will increase in higher elevation angles, so you can't really see it at the surface necessarily initially. But aloft, you'll see rotation start to increase first, usually. That is a sign that your storm is starting to rotate pretty hard. Then once you see that on the low-level scan, that is when you are starting to see that the low-level mesocyclone or low-level rotation is increasing, and that could be a precursor to tornado genesis.
I'm glad you added in that last part. I think it's one of the bigger mistakes we see, especially newer storm chasers, but definitely sometimes veterans as well make, is they will confuse a velocity couplet that's indicative of just a mesocyclone with a tornado that is currently on the ground. And that can cause, I think to put it mildly, you could say it could cause a little bit of an uproar within the communities. Just maybe as a bonus question here, Trey, how can people tell the difference between a velocity signature that's showing a mesocyclone versus a velocity signature that might be indicating a tornado is ongoing?
A lot of things go into that. Obviously, the stronger and tighter in spatial extent your couplet is, the better chance it has of being more of a vortex or more tornadic in nature. There's also a component of distance to the radar, which also leads into how high the rotation signature is in the atmosphere. If you're looking at a storm very far from the radar, you're not going to be able to see those low-level scans. So even if you see a very tight rotational couplet, but you're 70, 80, 90 miles from a radar site, that radar beam is looking well up into the storm. That's an indication of a very strong mesocyclone, not a tornado. We can't confirm a tornado just from that because we're looking way high up into the storm. If you have a storm that's closer and you're starting to see on the lowest elevation angle, if your storm is 10, 20 miles from the radar, and you're seeing that rotation strengthen in the low levels, that could be a sign that a tornado is about to occur or is occurring. Of course, we can confirm it with other radar products like correlation coefficient and whatnot to see if debris is actually being lofted. But those real tight couplets that are fairly tight in spatial extent and are very strong, especially those that are closer to the radar, those are signs that you may have a tornado that's about to be in progress or is in progress. You have to be careful again about distance from the radar as well and how high that radar beam is scanning in the storm.
Remember to check out those links in the description below and then watch another video.